AP5, angular momentum. This rather beautiful object is a gyroscope. So we have already got an equation that says that the torque is equal to moment of inertia times the angular acceleration. So T is I alpha. If you recall, that matches the linear equation F equals ma, force is mass times acceleration. Now alpha is defined as the rate of change of angular speed, so that's d omega by dt. So we can rewrite that equation as T equals d I omega over dt. That's just replacing the alpha with the d omega by dt. And that maps to the equivalent linear equation F equals d mv over dt. So rate of change of momentum. So mv here is linear momentum. So as you might expect, this version here, I omega, represents angular momentum. So angular momentum is I omega. If there's no resultant torque on the object, then the rate of change of angular momentum is 0. So that means I omega is constant. So if for something changing shape, or so its moment of inertia is changing, we could write that I1 omega 1 is I2 omega 2. So an example of that is somebody who is figure skating and spinning. So when they've got their arms out, they have a larger moment of inertia and a certain angular speed. If they pull their arms in, they reduce their moment of inertia. So as I decreases, omega 2 increases, so the skater spins faster. It's a very classic example of conservation of momentum, angular momentum. Units of angular momentum are a bit strange. So the equation is I omega. I, we know the units of I is kilograms meters squared, and omega is radians per second, so we have this rather clumsy set of units, kilogram meters squared radians per second. Or there is another version. If the object accelerates uniformly, and I mean in an angular sense, then we can say that torque is I omega over t, the change of angular momentum per second, per unit time. So we could rearrange that to write I omega is torque times time, tt, and torque, the units of torque are Newton meters, and of course units of time are seconds, so we end up with Newton meter seconds, which perhaps are a little bit easier to remember than that one. Newton meter seconds. Okay, if there's no resultant torque, then angular momentum is conserved, and that's the basis of a lot of problem solving. So the basic idea is that total angular momentum before some sort of change is equal to the total angular momentum after the change. Three basic circumstances. It could be an object changing shape, such as the skater we've already discussed. Another object mentioned in the textbook is a neutron star, which is a collapsing star. So its moment of inertia shrinks hugely, and its rate of rotation therefore increases hugely, so they're very rapidly spinning stars. Another circumstance is a rotating object combining with a stationary one. For example, if you drop an object on a turntable, then the turntable spins the stationary one up, and you can apply the equation in that circumstance. A third circumstance is where you've got two rotating objects combining together, or locking together, for example a clutch. Having said that, often when they give you an example with the clutch, one of the discs starts off stationary anyway. So we need to do a few examples of those.